Okay, so now we're going to look at a different kind of equilibrium. This is called Ksp. So when you put a solid in water, it's going to dissolve. So in this case, we'll get calcium ion and 2 fluoride ion. At this point, no more can dissolve. The solution is said to be saturated. So you're going to want to remember that calcium fluoride is a solid. It is not included in the equilibrium expression. So this is important. You're going to want to highlight this. So let's see how we would set up our Ksp expression in this case. So we're going to have the products here. So calcium, fluoride, and then your coefficient is going to become your exponent. So our Ksp is calcium ion times fluoride ion to the power of 2. And in this case, the value is 4.0 times 10 to the minus 11. The solubility product is an equilibrium constant and has only one value for a given solid at a given temperature. However, solubility itself is an equilibrium position and has an infinite number of possible values at a given temperature. This just means that it's going forward and backward all the time. Okay, so let's look at your first problem. Calculate the Ksp value for bismuth sulfide, and you're going to have to know your nomenclature. So here's the formula for bismuth sulfide, and we're given the Ksp. We're given the solubility is 1.0 times 10 to the minus 15. So we're going to set up our change plus 2x plus 3x. Again, our coefficients are going to be used this time. Our equilibrium is going to be 2x and 3x. So we are trying to find the Ksp. So here's our setup for Ksp for this question. Bismuth to the second power, sulfide to the third power. So first we're going to calculate the concentrations. We're going to use this, our 2x, to calculate the concentration of our bismuth. We were given the 1.0 times 10 to the minus 15. That's going to go in here. We multiply it by 2. We get 2.0 times 10 to the minus 15. Now we're going to calculate the concentration of the sulfide. That's going to be 3x. We're given the solubility here. We plug it in, and we get 3.0 times 10 to the minus 15. So now we're going to plug those values into our Ksp expression. So our Ksp is 2.0 times 10 to the minus 15 squared. We got the 2.0 for the bismuth. We put it in here. And then 3.0 times 10 to the minus 15 cubed. We got that for the sulfide. We put it in here. So we get 1.1 times 10 to the minus 73. That is our Ksp. Now, don't be afraid if you get these very small exponents. That's going to happen in these type of questions. Okay, so let's look at another kind of question. We're given the Ksp for copper 2 iodate is 1.4 times 10 to the minus 7 at 25 degrees C. So you would be given a question like this, and that's all you would get. You would have to set up your ice table yourself. You would start with the formula for the copper 2 iodate and put that in here. And that's equilibrium. You would have to do your stoichiometry. So copper is a plus 2, but we have 2 iodates because in the formula we had 2 here. Initially we have 0 plus x plus 2x. Again, we have to use the stoichiometry. Our equilibrium would be x and 2x. So now we're going to solve for our Ksp. I'm sorry, we're going to use our Ksp. There's our expression for our Ksp. It is equal to the copper ion times the iodate ion squared. So this is going to be x, 2x squared. So we use our equilibrium row and plug in our x and 2x. And then this squared was from our coefficient. So if we simplify this, it becomes 4x cubed. So we were given the solubility, we're given the Ksp, that's right here. So our Ksp equals 4x cubed. So we're going to solve for the x. You should have a button on your calculator. You're going to want to practice with that. So this is our x. It's called the solubility, or sometimes books will call it the molar solubility. Okay, so now we have another type of question. It's asking us to predict the relative solubilities of all of these salts. We're just going to start with group A here. So for group A, what they have in common is their Ksp equals x times x, where x is our solubility. So let's just do these one at a time. So the silver iodide Ksp was given as 1.5 times 10 to the minus 16. That equals our x squared. We solve for x. We have our copper iodide. We're given the Ksp. That equals x squared. We solve for x. And our copper sulfate has a Ksp of 6.1 times 10 to the minus 5. That's also x squared. We solve for x. So our x is in molarity. So all we do now is we compare the x's. So this is our most soluble. So that's why the copper sulfate is given on this side as most soluble. I'm looking at the number. And then this, so our copper iodide. And then our last one is the silver iodide. So you look at these molar solubilities and simply use them to put most soluble and so forth. Okay, let's do the other group. So for the other group, let's look at the equilibrium equations. So the copper sulfide goes to copper ion and sulfide ion. Its Ksp is x squared. So we're given the Ksp for the copper sulfide is x squared, and we solve for x. So when we look at the silver sulfide, we have some stoichiometry here. So that's how we get 2 silver ions and 1 sulfide ion. That's how we get the 2x and the x. So our Ksp is 2x squared times x. That simplifies to 4x cubed. So we plug in our Ksp value, equal it to 4x cubed, and we solve for x. Okay, so then let's look at the bismuth. Okay, so the bismuth has some stoichiometry involved. We get 2 bismuth plus 3 ions. We get 3 sulfide minus 2 ions. So we have 2x for the bismuth ion. We have 3x for the sulfide ion. So if we set up our Ksp, it would look like this: bismuth to the power of 2, sulfide to the power of 3, and we were given the value was 1.1 times 10 to the minus 73. So now we use our 2x that goes in here for the bismuth. We use our 3x that goes in here for the sulfide. The bismuth was to the power of 2. The sulfide was to the power of 3. So now we take all of this and we simplify. So it's 2 times 2, and it's 3 times 3 times 3, and that is how we get the 108. And it's x squared, x cubed, that's how we get the x to the power of 5. So if we simplify this and divide both sides by 108, that's how we get this. That equals our x to the power of 5. And then we get 1.0185 times 10 to the minus 75 equals x to the power of 5. You're going to want to find this button on your calculator. It is a button that looks like this. It has a little x over here. So you're going to want to use this button to solve for your x, and this is what you should get for x. So you're going to want to practice with that. So now all we do is compare the x's that we had, and if we look at their values, this was for the bismuth sulfide. This was for the silver sulfide. And this is for the copper sulfide. So if you look at the exponents, you would get the most soluble would be the bismuth sulfide, then the silver sulfide, then the copper sulfide. Okay, another type of problem will simply ask you to calculate the solubility. But in this case, we have a silver compound and a silver nitrate compound. You need to know your solubility rules. You need to know that all nitrates are soluble. So that's why this 0.1 molar is our initial for our silver ion. So I wrote it here so you could see it. So initially we have 0.100 molar silver ion. We have 0 chromate. Our change, we use the stoichiometry plus 2x, x. So now we just follow our directions. Our equilibrium is 0.100 plus 2x, and then for the chromate, it's x. We set up our Ksp expression, silver to the power of 2 from the stoichiometry, chromate. And we were given the Ksp, so we put it in here. Now we have to use our ice table to solve for x. So here's our Ksp. So this was for the silver. This was for the chromate. We can simplify and get 0.100 squared is x. And then there is our x. So the question asked what was the solubility? Our answer was 9.0 times 10 to the minus 10, and this is molarity. This is molar. Okay, so now we're going to look at how pH can affect solubility. So let's look at this system. We've got calcium oxalate. It has equilibrium with calcium ion and oxalate ion. So according to Le Chatelier's principle, as oxalate ion is removed by reaction with hydrogen ion, more calcium oxalate dissolves to replenish the oxalate ion. So let's look and see how that would work. So here's our calcium oxalate going to calcium ion and oxalate. The oxalate can react with H plus to make monohydrogen oxalate, which is a weak acid and therefore has an equilibrium. So essentially what you're doing to this system is you're removing the oxalate by adding hydrogen ion. And according to Le Chatelier's principle, if you remove a product, that will push the equilibrium towards the product. So now we have a question asking us about solubility in acid. Let's start with the barium sulfate. What you want to do always is set up your equilibrium expression. So barium sulfate in equilibrium with barium ion and sulfate ion. So when we have acid, the H plus would react with the sulfate and make monohydrogen sulfate, which is a weak acid. Therefore, you have an equilibrium. So what we're doing is removing sulfate. That pushes our equilibrium towards product. Therefore, the barium sulfate is more soluble in acid. Let's look at another situation. We've got lead 2 chloride in equilibrium with lead ion and chloride. So we're going to add the H plus. We get HCl. And since you already remembered or memorized your strong acids, you'll know that just breaks back up to give you chloride. So there is therefore no shift in equilibrium. That means lead chloride is not more soluble in acid. Let's look at the iron 3 hydroxide. It's in equilibrium with iron plus 3 and 3 hydroxides. If we have H plus, that will combine with the hydroxide and we make water. Water is a stable molecule. It's just going to stay like that. So essentially, we are removing hydroxide. We do have a shift in equilibrium. Removing product, our shift in equilibrium. Therefore, the iron 3 hydroxide is more soluble in acid. Let's look at the next system. We've got calcium carbonate in equilibrium with calcium ion and carbonate. When we add the H plus, we get carbonic acid, and carbonic acid spontaneously decomposes to water and carbon dioxide gas. The carbon dioxide is going to leave, so you are pulling away the carbonate. If you're removing product, you're removing the carbonate, you're going to shift the equilibrium this way. Therefore, the calcium carbonate is more soluble in acid. Okay, let's look at another problem. This is asking us about the quantitative effect of pH. We're going to compare the molar solubility of magnesium hydroxide in water to the molar solubility of magnesium hydroxide in a buffered solution. The pH is going to be 9 of this buffered solution. So let's just take this step by step. Let's just start with the water. Magnesium hydroxide is in equilibrium with magnesium ion and 2 hydroxide ion. We set up our Ksp expression. X 2x squared equals 4x cubed. We simplify, solve for x. So this x, 1.4 times 10 to the minus 4, is in water. Let's look at what happens in our buffered solution. So our pH is 9. And remember, pH plus pOH equals 14. So if our pH is 9, we can solve for pOH. Our pOH equals 5. So our pOH will allow us to put a value in for hydroxide. Our magnesium ion is still X. This hydroxide is from our pOH. So we set up our Ksp expression. Our Ksp is 1.2 times 10 to the minus 11. We're going to solve for X. We have to square the hydroxide because that comes from the stoichiometry. So in this case, in our buffer, our X is 0.12 molar. So that is our molar solubility in the buffer. Okay, so let's just go through this a little bit more in detail. So in water, the molar solubility is 1.4 times 10 to the minus 4. If we go back to our first table, our first calculations, that's where we got it. So our hydroxide equals 2x. So we're going to take 2 and multiply by the 1.4 times 10 to the minus 4. That gives us 2.8 times 10 to the minus 4. We can solve for pOH. We take the 2.8 times 10 to the minus 4, put it in our pOH expression. We get a pOH of 3.553. So we plug that in, solve for pH. Our pH is 10.447, and this is in the water. So just in the water, our equilibrium system would have a pH of 10.447. So remember, the buffer was at 9. So our pH in the buffer is less than 10.447, i.e. in the buffer solution. So when we have that pH, that means we have hydrogen ion, which can react with the hydroxide. So when our magnesium hydroxide is in, oh, that arrow should be the other way. Oh, I tried so hard to make this perfect, and I see I made a little mistake. We'll fix it. Okay, so that magnesium hydroxide is in equilibrium with magnesium ion and 2 hydroxide ions. But at a pH of 9, we have excess H plus, which can react with our hydroxide and then make water. And what you always want to remember about water is it's a stable molecule. So please fix that little, yeah. Okay, let me erase my little. Okay, so now we're going to use Le Chatelier's principle. So here is our equilibrium expression, or I'm sorry, our equilibrium setup. Magnesium plus 2 hydroxides. We add acid and we get water. We're pulling away hydroxide, so our equilibrium goes this way. So removing products, the equilibrium will shift towards the products in the buffer at pH 9. That means that magnesium hydroxide dissolves in a pH less than 10.447. So to recap, the pH of the magnesium hydroxide solution in water is 10.447 due to the dissociation of the magnesium hydroxide. Any pH less than 10.447 has enough H+ to react with hydroxide, removing product, shifting the equilibrium towards products. Okay, so we're going to stop here and we're going to start this on our next video.